Okay guys, here we are ready for the first set of notes for biology class. If you don't have things out already, you need paper and a pen or pencil. Also, get your paper ready if it's not already done. Just like we talked about just a few minutes ago. Wide right, skinny left. The topic, what is science? Chapter 1, Section 1. So as soon as you're ready, let's get to the road on the show. For as long as we've been around, humans have tried to answer questions about themselves and about the world around them in different ways. But what is science and what is it not? One thing we know, science is always changing. Although this book that we have is a treasure trove of facts and figures, as sure as I'm talking here, some of those facts will change in your lifetime if they haven't already changed. Science is not a collection of unchanging beliefs. So if the facts change and ideas change, what exactly is science? Let's take a look. Science is a way of observing, thinking, and knowing about the natural world. Scientists don't consider the supernatural, like ghosts. Science is also very organized. More about that in a minute. Science refers to a body of knowledge that has been gathered by the famous and the not so famous over hundreds and hundreds of years. So when we talk about science, we're talking about both a process and the body of knowledge. The next question that we consider is, what exactly is it that science wants to accomplish? What is its goal? This is really pretty simple. All objects in the universe are governed by universal natural laws, no matter what size. The ancient Greeks were some of the first people to try to view the world this way. So the foundation of science really goes way back. Scientists' goal then is, and was, and still is, to provide natural explanations for events in the natural world, and to use those explanations to understand patterns in nature and to make useful predictions about natural events. And we're going to be doing that all year long. So scientists look at the natural world and try to come up with a natural explanation. For as much as we know about the natural world, there is much we don't know, and much we will relearn because science doesn't stand still. Research and discovery often yields more questions than answers. So we not only strive to understand what we know, but we strive to understand what we do not know. Science aims for the best understanding that current methods can reveal. And as technology advances, so does science. Science also follows some pretty consistent procedures. You probably don't realize it, but you use scientific thinking all the time. When your car won't start, you think of obvious answers first. If those don't solve the problems, you start thinking of less obvious solutions. And if nothing you can think of works well, then you call the mechanic. In sports, cooking, lots of other activities, if you don't get the desired results, you analyze what went wrong and you try to fix it. Golfers adjust their swing, batters adjust their stance. You might add more flour or less salt or a little more baking soda. Any way you look at it, scientific thinking happens all the time, whether you know it or not. And all scientific thinking starts with observations, detailed and orderly, not random. These kinds of observations lead to questions. I wonder, what would happen if? Why does? A scientist will then make more observations to be able to make inferences or a logical interpretation. Police use evidence from a crime scene to make an inference about the suspect or motive. Scientists will then use this evidence and inferences to develop a hypothesis. A hypothesis is a little bit different than an inference in that a hypothesis can be tested and it can either be supported or rejected with the evidence. Every scientist has hundreds of hypotheses that they've made and that have been rejected or failed. When asked how it felt to have over 1,000 failures on his way to inventing the light bulb, Thomas Edison replied that he didn't have 1,000 failures, rather he had an invention that had 1,000 steps. If I wanted to see who was a better runner, girls or boys, would it be a good test to have some students run in the afternoon while others run in the morning? Some wear mass dress, others wear shorts and gym shoes, some inside, some outside? Why? I'm sure many people would be yelling that it wasn't a fair test. When scientists are designing an experiment to test a hypothesis, they have a few rules they follow to ensure that they're doing a fair test. And it's really pretty simple. They only change one thing at a time. This is called a controlled experiment. In a controlled experiment, as the name suggests, many things are controlled or not changed. In fact, whenever possible, only one factor should be changed. The factor that we change deliberately is called the independent variable, sometimes called the manipulated variable, because we manipulate it or change it. Edison kept trying different filaments in his light bulb, so for many of his trials this was the independent variable. If you're graphing your data, the independent variable is always graphed on the x or horizontal axis. The dependent variable then is the factor that we measure or observe after the changes have been made. For Edison, his dependent variable was the length of time the filament glowed. He wanted one that lasted more than a few minutes. The dependent variable is also called the responding variable because it responds to changes, and it is always graphed on the y-axis if you're graphing your data. An easy way to remember all of this information is to remember the phrase dry mix. Dependent, responding, y-axis, manipulated, independent, x-axis. Pretty easy. So when a scientist experiments, there's a control group with no factors or conditions changed and an experimental group with just one factor or condition changed. Study this diagram for a minute. What is the independent variable? What got changed? What are the controlled variables? What things did we keep the same to make it a fair test? Which group is the control group? If a scientist sets an experiment up correctly, other scientists can replicate the experiment to prove or refute its conclusions. This is the purpose of good scientific design. Another topic that scientists are absolutely bananas over is data. They make very detailed records of observations, and they can be divided up into two categories: quantitative and qualitative. Just as the names imply, quantitative data are numbers obtained by counting or measuring in some way. The date, how many, how much, all can be answered with a number. So that is quantitative data, quantity. Qualitative data involves quality or descriptions, and they usually cannot be counted. Color, direction, presence of other substances, these are all examples of qualitative data. Research tools that a scientist uses can be as simple as meter sticks or pH paper, or as complex as an electron microscope or a pH meter. Charts, graphs, and diagrams are also very important scientific tools in helping to collect and analyze data. Another aspect of data collection that scientists are very careful to consider are sources of error. Measuring tools have limited accuracy, and variations exist between tools. Also, data sample sizes must be very large. Larger samples allow for more reliability. Think of it this way. If I said the favorite show of most high school students was Mike and Mike in the Morning, but I only asked the football players I saw at practice one day, my results are not very reliable because my sample size is too small. A more reliable result is obtained by asking many more students of all ages and levels of involvement. The more times I do an experiment, the more reliable my results are. I'm sure you can think of some everyday examples of this too. Lastly, in scientific methodology, we come to conclusions. Finally! Experimental data can either support or refute a hypothesis, as we've said several times. The diagram to the right shows this process very well. If the data supports the hypothesis, then the hypothesis is said to be a valid conclusion. However, if the data does not fully support the hypothesis or totally refutes it, then that's not the end. This data leads to new questions, new experiments, and new data. In other words, the scientist develops a new experiment or modifies the existing experiment to try to prove his hypothesis. Edison did this 1,000 times in his search for a filament and a light bulb design that would stay lit for longer than a few minutes. If an experiment is not possible, then scientists look for other ways of testing hypotheses. Field studies and observations are common in biology because it's not always ethical or possible to experiment. Jane Goodall did this with her chimps and Diane Fossey did it with her gorillas. And sometimes ethics factor into the equation when we consider medical testing. We would not want to intentionally infect someone with a deadly disease as Edward Jenner did in 1796. So instead, we look for persons that have been exposed to conditions already thought to cause a disease, and we study them against people who have not been exposed. So testing is possible even when we can't test. And even with theories and laws that we have never ever been able to refute, when new occasions present themselves, we still test these hypotheses out. Scientists are skeptics by nature. One very well-known example of scientists continually trying to test scientific theories or laws happened with the moon landing of Apollo 15. Long ago, Galileo hypothesized that if two objects were dropped at the same time in the absence of air resistance, they should hit the ground at the same time. Newton and other scientists agreed that this should be true since gravity pulls with the same force everywhere. But until the 20th century, we did not have the capability of building a vacuum to test this. While Apollo 15 was on the moon, Commander David Scott performed a simple experiment. He dropped a hammer and a feather, supporting a centuries-old conclusion that objects fall at the same rate in the absence of air resistance. If the link to the video above doesn't work, just Google Apollo 15 hammer feather drop and watch the video. It's pretty cool. So this concludes the first section of Chapter 1. Look over your notes. Are there any parts that weren't clear or any questions that you thought of? Write those in the left-hand column. Any ideas or unusual thoughts about this topic? Write those in the left column. When we get back to the classroom, we're going to chat for a few minutes about your notes, and then we're going to talk about the Level 1, Level 2, Level 3 questions and the summary. So just sit tight and be patient, and we'll be getting on to the next step in a minute. See you later.